Hello class 11. Today what we are going to check is whether it is easier to pull or to push a roller. That is what we are going to check in this video. And of course we also are going to incorporate friction into it. So say for example you have a hand roller, okay, which can be of course operated with your hand. It can be either pushed or pulled. Okay, so this is the handle with which you either push or pull the roller. And at this instant, at this moment in time, the roller is in perfect equilibrium. So to say, I am not applying any external force, be it to push it or to pull it. So to say, the body, that is the roller, is static right now. So the two forces that is acting on it right now, the two forces are, of course, its weight mg, where m of course is its mass, and capital R, the normal reaction. Now since these two forces, they balance each other out, they are equal and opposite to each other, and of course they are acting along the same straight line. So therefore the total forces acting on the body is 0. The net force acting on the body is 0. So this is the scenario initially. Now say for example, let us deal with pulling the roller first. Okay. Now in order to pull the roller, what you do is you operate, or rather you apply a force in this direction. So this is the direction in which you apply a force. So this is the handle and you try to pull the roller. Okay, so you apply a force in this direction. So I will show the force here itself. Okay, let me not show it here. So my force acts along the handle itself. Okay, and this is the force which is acting. Now again, what we can do is, since force is a vector, this force can be resolved into two mutually perpendicular components. That is why I have told you resolution of a vector is a very important topic. So this force is resolved into two mutually perpendicular components. One of course along this direction. So this is the force, okay, in the horizontal direction, and its perpendicular component, it's along this direction. So this is another component of the force. Okay. Now if say for example this force acts at an angle theta, the force that we are applying acts at an angle theta with respect to the vertical, okay, then this vertical component of the force F is F cos theta. Alright, and the horizontal component of the force of course is F sine theta. Let us therefore see what is the role played by these two components of the force F. Let's look at F sine theta first. What F sine theta does is, because of F sine theta, the roller gets pulled, or rather it moves in this horizontal direction. When we are trying to pull the roller in this direction, of course we are applying the force in this direction, but the roller is not going to pull, not going to get pulled in this direction, of course. The roller is going to move in this direction. So therefore it is done actually by the F sine theta component of the force. Also let us see what F cos theta does. Let me tell you at the very beginning, what F cos theta does is, F cos theta decreases the weight of the roller. Let us see how. As you can see, F cos theta acts in the direction of the normal reaction. So to say, the total force in the upward direction is R plus F cos theta. Okay, so when we are applying this force of pull, so to say, R plus F cos theta is what is balancing the weight of the body. Or so to say, R is equal to mg minus F cos theta. So you see, initially when there was no force of pull acting on the roller, the normal reaction was simply equal to mg. But when we apply the force of pull, of course along the direction of the handle, what happens is the normal reaction is decreasing. And we already know that the weight of a body is actually equal to the normal reaction of the body. Whatever is the value of the normal reaction, that is the weight of a body. Okay, take for example a freely falling body, this piece of chalk. It has a certain mass So therefore it has all the while force of gravity acting on it. Force of gravity mg is all the while acting on it. But we always say that for a freely falling body its weight is 0. Why? Because for a freely falling body there is no normal reaction. Although the force of gravity mg is all the while acting on it. Do remember that. So whatever is the value of the normal reaction, that is the value of the weight of the body, mind you. So here we see, once we apply a force of pull F in this direction, the normal reaction decreases, therefore the weight of the body decreases. Let us also give a look at the case of pushing a roller. Let us see what happens. So this is a roller here. Alright. So this is your roller. So this is your roller. So when we are not applying any force on the roller, there are two forces acting on it. Mg of course and the normal reaction. At this instant R is equal to mg, don't forget. Here is a handle. This is the handle. Now what we do is we apply a force of push on the roller, and the force of push is acted in this direction of course. So this is your force of push, or rather let me show this force in this direction here. So here is the force acting. Since force is a vector, don't forget, keeping its 90 direction fixed, I can take the vector anywhere in space. Alright, so here is, this vector is denoting the force. Again, this force can be resolved into two mutually perpendicular components. One is in this direction, and of course the other is in this direction. So this is the force. Now again, if theta is the angle of the force with respect to the vertical, mind you, so this force is F sine theta, and this component of the force is F cos theta. Alright, so what is happening now? So when we apply this force F, the force of push F, what happens is the normal reaction R, so to say, is equal to mg plus F cos theta, because F cos theta is acting in the downward direction. So you see that the normal reaction effectively is increasing. So to say, the weight of the body is increasing. And what is F sine theta doing? Because of this component F sine theta of the force, the roller moves in this direction. Okay, so from this scenario itself, from this explanation itself, we can understand that when we are pulling a roller, since its effective weight is decreasing, so it will be easier for us to pull a roller. And when we are pushing a roller, its effective weight is increasing. So therefore it will be difficult for us to push a roller than to pull it. Alright? We can also incorporate friction in here. Why? Because we know F of S is equal to the coefficient of friction into the normal reaction. So therefore, I'm dealing with the case of pulling a roller first, okay? So F of S is equal to, in this case, mu S into mg minus F cos theta. So you can also give an explanation in terms of the force of friction, because we are seeing when we are pulling a roller, the force of friction is also decreasing. Whereas when we are pushing a roller using the same equation, of course, so mu F of S is equal to mu S into R, and the value of R is mg plus F cos theta. So looking at these two expressions for the force of friction, we see that when we are pulling a roller, the force of friction is lesser than the force of friction when we are pushing a roller. So this also, therefore, you can say in terms of the force of friction, therefore we see that it is easier to pull a roller than to push it. Thank you, class 11.